Hey everybody, I wanted to give a few hints on this problem. Hopefully this helps you out if you've been struggling on it. It's sort of a tricky one. But the purpose of the problem really is to start to get you to think about what it means for a transistor to act like a voltage-controlled current source and how that can be used to amplify signals. So on the left-hand side, we have our MOSFET amplifier circuit that we're analyzing. There's this input voltage Vs of t and an output voltage V out of t. And on the right-hand side, we have the equivalent circuit model of the transistor replacing the MOSFET. So we have this voltage-controlled current source, and what it does is it defines the output current IDS, and it's a linear relationship between G and VGS, the voltage between the gate and the source. G is known as the transconductance. And in this problem, that's given as 2 amps per volts. So this equation, by the way, implies that there's a linear relationship between the drain current and the gate voltage of a transistor for any voltage. Now, this is not the case for MOSFETs. In fact, large DC voltages in general don't have this linear mapping. But for this problem, we just want you to start thinking about what it means to be a voltage-controlled current source. So just keep that in mind, that it's not always a linear relationship. Okay? So that's what's going on over there. So let's talk about what Vs of t actually is in this problem. So here are my axes. I have time as my x-axis, and Vs of t is my y-axis. And we're given Vs of t in this problem. Vs of t, I'm going to change my color for this, is equal to 0.5 plus something else. Now let's look at what 0.5 actually looks like. So I'll draw a dotted line here at 0.5. That's what a DC voltage of 0.5 volts looks like. Looks like our input has this DC 0.5 volts as part of it. In the other part, I'll switch to blue for this one, 0.01 cosine of 1,000 t. Okay, and what does that normally look like? Well, that looks like this little cosine down here. My axis is bumpy, but hopefully you can tell what's going on here. And its amplitude is 0.01. Okay. So it's this little sine wave, and the sum of the two gives us Vs of t. So now back to black. The sum of these two signals looks like this. Looks like the cosine wave brought up, level shifted up to 0.5 volts. Okay, so that's that voltage that we have here. The first question on this problem asks you, what is the current entering the gate of the transistor? To answer this, we have to look at the equivalent circuit model, and it should be easy to see that there's an open circuit. There's no path for the current to flow, so Ig equals 0. So that's a freebie. That's the first answer to this problem, is that the current entering the gate is 0. Now, think about what that means. If no current is entering the gate of the transistor, that means that this voltage Vs of t appears at the gate. There's no voltage drop across the resistor. So that means VGS is equal to Vs. Okay, well, we know what Vs is. So now we can start to talk about what IDS is, because IDS is simply G times VGS. Now, I'm not going to continue doing the math here, but I just want to keep talking about the problem. So IDS is a function of time, And generally, it is going to have a DC component and an AC component. So the DC component we denote capital I, capital D, capital S. And the AC component we use all lowercase. Lowercase I, lowercase d, lowercase s. So when we multiply the transconductance by VGS, we're going to be multiplying the transconductance by this DC part to get the DC current at the drain. We're going to be multiplying by this AC component at VGS to get the AC current at the drain. Now, these two currents come into play and become important when we talk about the output voltage. Okay, so first let's think about what IDS does. So a voltage at VGS will cause this current to change. And as that current changes, that current goes through this resistor RD. And that changes the voltage drop across that resistor. So the output voltage V out of T consists of this DC voltage VDD. Let's go ahead and write it in red. Minus the DC voltage drop across that resistor, which is going to be IDS times RD. But there's also the AC voltage drop across the resistor. So we also have to subtract IDS times RD. Okay, so there's going to be this DC level at the output. All right, so let's plot V out of T. Okay, so V out of T has this DC component right here. This DC output voltage level, which is VDD minus IDS RD. And there's this minus IDS RD. So that probably looks something like this. And there's a little bit of gain. You see the sine wave, or the cosine has expanded in its amplitude slightly. So the actual output voltage looks something like this. Okay? So this is now V out of T. And what we're interested in isn't how the DC level shifted, but how the AC level shifted. So when we ask for voltage gain at the end, we're interested in the ratio between this amplitude and this amplitude. So I know it's a lot of math, but hopefully this problem helps you start to wrap your head around the idea of amplification being performed by a MOSFET transistor.